In previous years, F1 cars have used suspension systems that have allowed the rear end to drop quickly on the straights but stay high in the corners. But how does this work and why do they want to do it? In this video, we're going to go through why F1 teams wanted to use these sorts of suspension systems on their cars and how they work, as well as touching on why they don't seem to be important with the new 2022 regulations. For those of you that are new to my channel, I was an aerodynamicist for Mercedes for the 2018, 19 and 20 Formula 1 seasons. I now work as an aerodynamics consultant, designing race car aerodynamics kits for cars in different classes all around the world. Before we get started, it's probably a good idea to go and watch my video on how heave springs work first, so you can get an idea for the sort of suspension systems we're going to be discussing, as we're going to spend most of this video talking about how the heave system on F1 cars works. Anyway, let's get into it. To start with, why do the teams want to have the rear drop in the first place? Well, it all comes down to aerodynamic performance. Essentially, you want to run the car at maximum downforce in the corners, but then you want to run it at minimum drag on the straights. The previous generation of rules allowed the cars to run at very high rake, i.e. the wheels very low with respect to the car. I touch on the mechanisms a bit for this in my porpoising videos, but what we're mainly looking at is the fact that this rear cake tin here, as well as more advanced floor edge detailing than the new rules allow us to run the car at a very high ride height and get most of our downforce at that high ride height. And that's why we saw so many cars running at high rake. Now, at higher ride height, two things happen with the car. One is that the high rear ride height forces the car to be more angled, like this. With that extra angle, all the surfaces of the aero on the car are angled a bit more and all have a bit more angle of attack. So things like the rear wing and the underfloor and the front wing, they'll all be at a little bit more angle, which means they get a bit more downforce and they also get a little bit more drag. As the ride height levels out like that, all the angle on these devices back off, so their downforce and drag reduces. At the same time, this rear wheel rises with respect to the main body. And as that wheel rises, the distance between our little cake tin winglets here and the main diffuser floor increases. And this can significantly change the interactions between the winglets on the cake tins and the lower rear wing end plate and the remainder of the diffuser and floor edge. And this changes how the tire wake is managed around the rear of the tire, which can have significant effects on the drag characteristics. So overall, what happens is that at low ride height, we get much less drag on the car. And F1 cars of this generation could drop around about 10% of their drag between their high and low ride height states. A lot of people seem to mention dropping the rear ride height makes the diffuser stall and that saves the drag. And that's not usually the case, because what happens is that if you stall a diffuser on this style of F1 car, it's generally speaking undesirable. Usually the stall happens on the inboard boat portion, and all that happens is that it means that you may or may not get your rear downforce coming back under brakes, and therefore the drivers don't like it because it's quite unpredictable in terms of handling. You don't want to encourage a diffuser stall on these cars. So these cars drop their drag without having any stall or separation. So that's why we want our rear suspension to drop quickly when we get onto the straights. But how do we get it to drop quickly when we get onto the straights? Now what we have to do is consider the effects of downforce with speed. So typically speaking, if we have speed on the bottom axis and downforce on the side axis, the vertical axis, what will happen is that downforce will go up like this with respect to speed. Now, if we have a spring here like that, the spring will compress at a rate of distance equals the force divided by the spring constant, K. Now, spring constant K varies from spring to spring. Basically, a stiffer spring will have a higher value of K. And this spring rate will stay roughly the same regardless of how much I compress this spring. So even if I add a bunch of preload to the spring, it'll still use the same spring rate. Now, the force on our car won't just be the downforce, there'll be a component of weight too. So there'll be the weight of the car, and then as we go up in speed, the downforce will be kicking in. Now, if we say that this here is our highest cornering speed on track, what we want to do is we want to have it so that north of here, our suspension collapses, as we discussed before. But with a conventional spring rate, a linear spring with a constant K, what will happen is that the spring will collapse at the rate that the force is increasing, as we can see here. So if we would draw the same plot as a spring displacement with force, so the force is our purple plot, what would happen is it would look exactly the same like that. But we actually don't want it to look like that. We want it to look like this, and then we want it to step rapidly and then move like that. And that way we can maximize the drag benefit through this whole region here by having it drop quickly. So what we want is a spring that above a certain force collapses quite rapidly. And of course, to achieve this effect, what it means is that I basically have to have my initial spring rate through this bottom portion along here, and then have this portion from here to here being a very low spring rate, and then I need to go back up to a high spring rate to control the travel once I get to the bottom end of the travel, whether that's a high spring rate or a bump stop at this particular end of the travel. And let's look at a demonstration of how that is achieved. What I've done is I've printed up a little 3D printed rig to demonstrate how you can use a dual rate spring system to achieve variable spring rates throughout the travel range. Now what we've got here is a central shaft, and on that central shaft you'll notice that there's this little notch here. Now the idea is that what I can do is I can put a collar on here. When the collar slides to the top, it'll be stopped by this notch. So I've got here a spring, and what I'll do is I'll put my spring on the shaft, and then I'll put my collar, which has a little mating bit for the spring, around here. The spring goes in, and you can see the spring is contained like that. Now this is my soft spring, but what I can do is on top I can put what I would consider to be my stiff spring. Now this spring is 4 times stiffer than this rate, is a spring rate 4 times higher than this spring. And then what I've got is I've got a little plunger at the top to actuate the whole thing. So you can see I press that and the springs compress. And you can see that right now the springs are both compressing at the same time. We're basically getting the spring rate of these 2 springs all combined into one unit. But what I want to do is start playing around with the preload on this first spring and show you what happens. So to increase the preload, I've got these little spacers here, and the idea is that you can put those in on top of the spring. So if we pull out the little cap and we grab a spacer, we can put the spacer there like that, and it goes around the shaft. And then now we have a more preloaded spring that is then restrained by the notch up there. So then when we go and put our stiffer spring on top, you can see that we have a tiny bit of preload that we've got to overcome before the whole system moves. Now let's go a little bit more extreme. Let's add another spacer. And you can see this is it with quite a lot of preload. So you can see that at the initial portion of the travel, when I'm just pressing the top, all we see is this top portion move. The bottom portion is not moving. This spring is not compressing at all. This spring is showing all the compression. I then press a bit harder and we overcome the preload of the soft spring at one point, and then it starts to move down quite rapidly for each bit of force. Eventually, this plunger is hitting the notch there, so it can't travel any further, and the system is stopped. But what if we preload it so that this spring here binds up fully? So currently you can see that this spring isn't binding up at all. Well, what if we preloaded it such that at the bottom of its travel, that spring was binding up? We can see here that we've got this bottom spring really quite heavily preloaded compared to the top spring. And I go and push on the plunger, you can see that all the deflection is coming from this top spring. So you can see there's no movement at all in the bottom spring. It's all from the top spring. Then if I exceed the force required to get past the preload of the bottom spring, all of a sudden it moves down until that binds down there. So that spring is coil bound. And now I can still move the top spring up and down. And this will actually be at its initial spring rate. So you can see here, it's at a certain spring rate. We push it down and the bottom coil gets fully bound, which puts the top spring back to the original spring rate. So basically we have our relatively high spring rate at the top, a very soft spring rate through the mid portion, then we're back to our high spring rate at the bottom, and then we go on to the bump stop if we keep pushing further. So in this particular case, we hit the shaft just here. So you can see that I've managed to, from a very simple device, get effectively 3 different spring rate zones. But the key thing is that I've got a spring that stays stiff at the high end of travel, then blows through the travel really quickly, and then stiffens up again at the bottom. Now, of course, on that generation of cars, they're not using that exact spring system. What they'd be using is more like a gas or a pneumatic hydraulic setup that allows them to precisely control how this particular force is kicking in when the suspension is collapsing, and allow them to vary this very precisely from track to track. And also allows them to get a huge difference between the preloaded and unpreloaded spring rate. So why don't they seem to be using them this year? Well, firstly, there's no pneumatic hydraulic springs allowed this year. You've got to be purely mechanical. However, it's worth noting that, as I demonstrated, you can pull this off with just a mechanical setup. The bigger thing that affects it is more the fact that the new aero rules, as I've previously discussed, don't encourage a high rake car behavior. So you naturally want to run the car low already for best performance. So you're going to be running it low at the start of the straight and for the corners, as well as low during the straight. And this just means you end up with a very high spring rate all round, but you don't need a dual rate system as we see here. Well, that's all for this video. Thanks for watching. If you enjoyed it, don't forget to like, comment, and subscribe. And hopefully, I'll see you next time.